Hello and welcome to this presentation related to heat transfer through composite walls. An illustration of a composite wall is shown on the right hand side here of thickness x1, x2 and x3. In a previous presentation we calculated the heat transfer through a single wall. In this presentation we're going to calculate the heat transfer symbol Q using this formula shown here for the composite wall. It is strongly encouraged that you review the previous presentation on heat transfer through a single wall before reviewing this presentation related to heat transfer through composite walls. Here's a presentation overview. We commence with an introduction outlining the formula used to calculate transfer of heat energy through composite walls. This is the formula shown here. Then we have example 1b. This shows how to calculate heat transfer Q through a composite wall, having a range of temperature from T1 to T4, shown here on our sketch. And we also show how to calculate the intermediate temperatures, T2 and T3, within the wall, shown here on our sketch. Next we have exercise 1b, calculates the heat transfer Q and the intermediate temperatures T2 and T3 through our wall. Then we have some questions for you to undertake. Question 1b calculates heat transfer Q, as does question 2b. And question 3b calculates the heat transfer per unit area. We use the symbol lowercase q to denote that property. And also how to calculate the thickness x2 of the composite wall. Full work solutions are shown to the exercise and the questions. The presentation concludes with some further questions for you to attempt at your own pace. And here are the approximate start times related to the various sections contained within the presentation to hopefully aid your ease of access through the presentation, but please note these times are generally rounded to the nearest minute. I've just included this slide within the presentation. It's a recap slide. It's actually an extract from the previous presentation. It shows the formula Q is equal to KAT divided by X, which calculates the heat transfer Q through a single wall. The nomenclature is shown here for reference. We will be referring to this formula within some of the calculations we're going to undertake. Let's now consider the transfer of heat energy through composite walls. On the left hand side shows our composite wall with heat energy Q passing through the wall. And the composite wall has three sections. Section 1 shown here of thickness x1, section 2 shown here, thickness x2, and section 3 shown here, thickness x3. So for equilibrium conditions, the transfer of heat energy through each section of a composite wall is assumed to be the same. So in other words, in our diagram, the heat transfer through section 1, Q1, would be the same value as the heat transfer through section 2, Q2, and the same value as the heat transfer through section 3, Q3. That's the assumption made in the calculations. Thus, when considering the heat transfer through composite walls, shown in figure 1, the formula for Q is as stated below. The heat transfer Q is equal to the area of the wall multiplied by the difference in temperature between T1, shown here, and T4, shown here. And that's all divided by, in this bracket, thickness x1 divided by the thermal conductivity coefficient of material 1, labelled K1, added to x2 divided by K2, added to x3 divided by K3. Obviously, if we had only two sections within our wall construction, we would have T1 minus T3, and we would ignore the x3, K3 from the formula. So you'll see that the formula shown here for Q will be slightly modified depending on the configuration of the composite wall. So transfer of heat energy through the composite wall continued. Here's the nomenclature used. It's almost identical to that we used in the previous presentation. Just notice the temperature difference now is not simply T1 minus T2 for a single section wall. It might be T2 minus T3, T3 minus T4, etc., depending on the calculation we're undertaking. But essentially that's the nomenclature we'll be using throughout the presentation. And for reference, Table 1 shows average values of coefficients of thermal conductivity. The left-hand side is the particular substance. On the right-hand side are the coefficients of thermal conductivity having the unit of watt per meter per K. This table is purely included for reference. You can obviously research your own values for the various substances shown here, but some of the questions we're going to consider might refer to the contents of this table, so extract the appropriate information as required. And of course, the thermal conductivity coefficient has a symbol K within these notes. Here's the full listing of the table. Let's consider example 1b. So a brick wall of thickness 225 millimeters is faced with concrete 25 millimeters thick on the outside and plaster 12 millimeters thick on the inside. So here's our brick wall of thickness XB. Here's the concrete on the outside of the wall, thickness XC. And here's the plaster on the inside of the wall, thickness XP. We're asked to calculate the heat flow rate through the wall if it is 6 meters long and 2.5 meters high. The temperature on the inside surface is 21 degrees C, labelled that as T1 here. Temperature on the outside surface is 7.2 degrees C, shown here, labelled that as T4. We've got to determine the intermediate or interface temperatures T2 and T3, shown here. So initially we'll be using this equation to calculate heat transfer Q for the 3-section wall as shown in the diagram. And then we'll be using this equation, rearranging this for the change in temperature, in this case shown as T1 minus T2, to calculate the various intermediate temperatures on the wall. I'll show you now the full work solution for example 1b. So example 1b, here's the beginning of the solution. First, as always, we need to extract information from the question, and also in this case from table 1 in our notes, and shown on the previous slide in the presentation, because we need to find the thermal coefficients for the plaster, the brick and the concrete. But initially extracting information from the question, the thickness of the plaster XP is 12 millimeters in the question. Notice I've immediately stated that in meters because I'm going to use meters throughout our calculations. So that's 0.012 meters. The thickness of the brick, stated in millimeters in the question, that's 0.225 meters. And the thickness of the concrete, stated in the question, is 0.025 meters. In our diagram here, here's the plaster section XP, the brick section XB, and the concrete section XC. We're given in the question the length of the wall in meters, the height of the wall in meters, so we can calculate the area of the wall, and it's 15 meters squared. Next we need the coefficient of thermal conductivity for the plaster Kp, and that's 0.45 watts per meter per Kelvin. If we refer to table 1, find plaster in the table, we can see it's 0.45 watts per meter Kelvin. The K for the brick is 0.6 watts per meter Kelvin. And again, from our table for the brick, here's its thermal conductivity. And the K for the concrete is 0.85 watts per meter per Kelvin, shown here in our table 1. The temperature difference is T1 minus T4. So T1 is 21 degrees, that's the inside temperature, and T4 is 7.2 degrees C, and that's the outside temperature. So our change in temperature is 13.8 degrees C. So that's the information extracted from the question and from, in this case, table 1. Example 1b, the solution continued here. So firstly, let's calculate the rate of heat transfer, or the heat flow rate Q, Showing the formula on the left hand side here for Q. We're now just going to insert the various values. For convenience, I've shown the various values on the top right hand side of our slide here. So we're just going to literally insert them into the formula. So our area is 15 meters squared. In this case, temperature T1 minus T4 is 13.8 degrees C. XP upon KP. XP shown here. KP shown here. Next, XB divided by KB. XB shown here. KB shown here. Insert them into our equation. And finally, XC divided by KC. XC and KC. Insert those values into the equation. Evaluating Q is 480 watts. And of course, we assume now that value of Q is constant throughout the three sections of the composite wall. So that's the solution to the first part of example 1b. Example 1b, solution continued. Now we need to determine the intermediate temperature T2 within our composite wall. So this is part 2. So to determine the intermediate temperature T2, we're going to use the equation from the previous presentation related to a single section wall. And that was basically this: Q is equal to KAT divided by X, where the T is actually the temperature difference. So this is the formula: Q is equal to K A capital T, which is T1 minus T2, all divided by XP. So we now need to transpose the equation for T2. So to go through the process here, the first thing I've done is to divide both sides by KPA, as shown here. And then next I've added T2 to both sides of the equation, and then I've subtracted the QXP divided by KPA from both sides of the equation. So my transpose formula in this case is T2 is equal to T1 minus the Q multiplied by XP divided by KPA. All I'm going to now is insert the values. Again, they're listed above for our convenience here. Evaluating, T2 is 20.15 degrees C. We're now going to apply the same approach to calculate intermediate temperature T3. Example 1b, solution continued. So now in part 3 we have to determine the intermediate temperature T3, shown here. It's a very similar approach to that for calculating the intermediate temperature T2. The only thing that's different now in our formula of heat transfer Q is that we now use the K value for brick and the XB value for brick, because that's the section through which the change in temperature we're considering. And the temperature difference will now be T2 minus T3, shown here. So essentially, using the same transposition as shown on the previous slide, we can evaluate the formula for T3, and it's T2 minus Q multiplied by XB divided by KB multiplied by A. So inserting the values, the intermediate temperature T3 is 8.15 degrees C. Example 1b, solution continued. I just included part 4 here for reference really. I'm determining the outside temperature, T4. We know it's 7.2, but it's just basically a check calculation on my previous calculations. I won't labour this with you, but again I've taken the equation for Q, but this time having the change in temperature T3 minus T4 because I'm considering the concrete section. So my KC and my XC will be for concrete this time. Area remains the same, of course. So I've just transposed the above equation for T4 and inserted the values, and it works out to one decimal place to be 7.2 degrees C. So that was correct. So that was just a check calculation added for reference. Here's exercise 1b. The solution is very similar to that of example 1b. So I'm going to very briefly outline the question. I will show you a solution, but I'll let you review the solution at your own pace. So here a cavity wall is constructed of two masonry walls, but they're separated this time by an airspace. The outer wall is made from brick, the inner wall is made from reinforced concrete, and we have this air gap between the walls. If the brick has a width of 63.5 millimeters, the reinforced concrete a thickness of 100 millimeters, and the air gap between them is 30 millimeters. We've got to calculate the heat flow rate, that symbol Q, through the cavity wall if the wall is 7 meters long and 3 meters high. We're given that the temperature of the inside surface of the reinforced concrete wall is 22 degrees C and the outer surface of the outside brick wall is 2.5 degrees C. We're asked to determine the interface or the intermediate temperatures through the cavity wall, and we're given the K values for brick, for the reinforced concrete, and for air in terms of watts per meter per Kelvin. The answer for heat flow shown here, and for the intermediate temperatures T2 and T3 shown here. I'd encourage you to start the presentation and attempt exercise 1B. It's a very similar solution to that of example 1B, so you can use example 1B as your template, but I will outline the full solution on the following slides. So exercise 1B, commencement of the solution. As always, the first thing to do is to extract the information from the question. I'll let you review this slide at your own pace. Notice the temperature difference here, T1 minus T4, is 19.5 degrees C. So exercise 1B, solution continued. As always, I add a sketch of the scenario we're considering here, the composite wall in this case. Just note for your reference, this sketch is not actually drawn proportionally. If I sketched the diagram appropriately, it would have looked more like this. But anyway, just having a sketch of the problem helps with clarity and understanding of the solution required. So firstly, I've calculated the rate of heat transfer, Q, and my calculation is shown here. Again, I'll let you review this at your own pace. But Q evaluates to be 315 watts. Exercise 1B, solution continued. Here's part 2. We're calculating the intermediate temperature, T2, shown here on the diagram. And again, the transposition is the same as that shown in example 1B. So I'll let you work through a solution for calculating T2, 21.4 degrees C here. And exercise 1B, solution continued, part 3. We're finding the intermediate temperature, T3, shown here. I'll let you review this solution at your own pace. Transposition for T3, very similar for that for T2. The value of T3 is 4.1 degrees C. Exercise 1B, solution continued. I have included a step 4, which again is a check. I'm calculating essentially the outside temperature T4. We know from the question it's 2.5 degrees C. So when I evaluate T4, it's approximately 2.5 degrees C. So I consider my calculations to be correct within the accuracy required for this type of problem. Let's now consider some tutorial questions related to heat transfer through composite walls. Question 1. A Dural tank has a wall thickness of 10 millimeters. We're asked to calculate the heat flow rate through the tank when the inside and outside surfaces of the tank are at temperatures of 80 degrees C and 18 degrees C respectively. If the outside wall of the tank is now covered with a fiberglass sheet of thickness 5 millimeters, so that the outside surface of the fiberglass is at a temperature of 18 degrees C, what would then be the rate of heat transfer through the materials of the composite wall? We're given the K value for Dural and for fiberglass. Finally, we've also got to calculate the reduction in heat transfer due to the addition of the fiberglass sheet to the Dural tank. Answers are shown in the bracket here. Just notice that the values of Q here are calculated in terms of unit area because question 1 does not actually state the geometry of the wall itself. If it helps, is a sketch of the Dural and fiberglass composite wall. But I would now encourage you to start the presentation and attempt question 1, although I'll briefly outline the full work solution on the following slides. There is question 1, commencement of the solution. On this slide I've simply extracted the information from the question, which I'll let you review at your own pace. As always, ensure your dimensions are in meters and I've calculated the temperature difference T here, which is the same in both parts of the question, but I've denoted it as T1 minus T3 here, and that would be 62 degrees C. Solution continued. So part 1, I've calculated the rate of heat transfer through the Dural tank per metre squared. This is when there's no insulation. I've labelled this as lowercase q1 because we're calculating heat transfer per unit area. So q1 is equal to kT divided by x. Inserting the values, it's 1.302 megawatts per metre squared. And part 2 here, now calculating the rate of heat transfer through the fiberglass insulated tank. I've labelled that as lowercase q2 here. This is now a composite wall, so we now consider our temperature difference T1 to T3, which is actually the same in this case. It's still 62 degrees if you read the information in the question. But I've got to account now for both the Dural and the fiberglass in my calculation. Inserting the values, the rate of heat transfer is 2.352 kilowatts per metre squared. Finally, we're asked to calculate the percentage change in heat transfer per metre squared here. In my calculation here, that will be Q2 minus Q1, or divided by Q1. Inserting the values from above. For the formula I've used here, the change in heat transfer is actually a negative value. That just means it's a reduction. So a 99.8% reduction in heat transfer by adding the fiberglass sheet to the outside of the Dural tank. So a very substantial reduction by adding the insulation. Here's question 2. I'm going to let you review this at your own pace. It's a very similar solution to that of question 1. Just note the temperature difference is stated as 8K. Don't let that bother you. We know from our previous work that the increment between the Celsius degrees C scale and the absolute Kelvin scale are the same. So 8K is the same as 8 degrees C. And again, all the information is given in the question you need to solve the problem. I'd encourage you to stop the presentation, attempt question 2, but I'll outline the solution on the following slides. Question 2, commencement of the solution. Just extracting information from the question here. Just be careful that dimensions were given in terms of centimetres and millimetres here, so be careful with your conversions to metres. As I said previously, the temperature difference T is stated as 8K, but of course that's the same as 8 degrees C. Specifically given the area of the wall in this particular case. Question 2, solution continued. The first part of the question calculated the heat transfer through the tiles that are insulated with felt. So Q for the tiles in felt is 9.36 kilowatts. Secondly, calculate the heat transfer through the tiles only. That's with no insulation, of course. So Q for the tile, 14.98 kilowatts. Finally, calculate the increase in heat transfer, assuming the felt was not used. And that calculated to be a 60% increase. Question 3. Given that a compound wall consists of a layer of fire brick 36mm thick and a layer of fiberglass 22mm thick, we've got to find 1, the rate of heat transfer Q for the wall and the temperature of the interface T2 when the temperature of the outside surface of the fire brick T1 is 450 degrees C and that of the outside surface of the fiberglass T3 is 15 degrees C. And part 2, we've got to determine the thickness of the fiberglass required to ensure that the temperature drop across the fire brick, in other words that's T1 minus T2 in our notation, does not exceed 60 degrees C. And thus we then have to determine the new Q value for the revised wall configuration. We're given the K value for fiberglass and for fire brick in the question. The answers are shown in the bracket here. For part 1, the heat transfer rate Q, notice it's shown in terms of heat transfer per unit area because no area is actually given in the question. Here's temperature T2 for part 1. And for part 2, the fiberglass thickness is stated here and the revised value of heat transfer Q stated here. Part 1 of the question is very similar to that we've encountered in the previous solutions of this presentation, but for part 2 we use the assumption that the heat flow rate per unit area through the brick is the same as the heat flow rate per unit area through the fiberglass. So we essentially equate these two equations shown here for the brick and the fiberglass, and we'll need to rearrange the equation to find the value of XF, that's the thickness of the fiberglass required for the conditions stated in the question. So I'd now encourage you to attempt question 3, certainly the first part of the question you've encountered before, but as I said, the second part of the question may need some further consideration. I will outline the full solution to question 3 on the following slides. So question 3, here's the commencement of the solution. On the left hand side I've drawn a small sketch, a compound wall showing the brick and the fiberglass. As always, I'm extracting the information from the question here. Question 3, solution continued. So firstly, I've calculated the rate of heat transfer through our fire brick and fiberglass per unit area, because no area was actually stated in the question. So calculating lowercase q here, this is the value in watts per meter squared. And then next I've determined the intermediate temperature T2 on our diagram. Not very clear to see, but it's this temperature here on the diagram. And again, same approach as before, commencing with our equation for heat transfer per unit area. I've rearranged the equation for T2. So intermediate temperature T2 is calculated here. I did undertake a check here, this is just for reference really. Instead of using T1 and T2 as my temperature difference, I've now used T2 and T3 given the parameters in the question. And of course that works out to be exactly the same temperature for T2. So I can now calculate the temperature drop across the fire brick, and in this case that's T1 minus T2, which evaluates to approximately 85 degrees C. Question 3, solution continued. So here's part 2. This is the part of the question where we have to determine the thickness of the fiberglass XF. If the change in temperature, stated as delta T here, across the brick is limited to 60 degrees C. So from our previous calculation we found the change in temperature across the brick was approximately 85 degrees C. Now we have to limit it to 60 degrees C. So we can now calculate T2, the intermediate temperature, because we know the inside temperature is still 450 degrees C, that's our T1, and the temperature difference across the brick must be limited to a maximum of 60 degrees C. So that means we can evaluate T2, which is 390 degrees C. So now using the assumption that QB is equal to QF, that's the underpinning assumption we've used throughout the presentation. So we can now use the formula for a single section wall, the generic KAT upon X. In this case we ignore the A because we're calculating heat transfer per unit area. So we can write that equation in terms of the brick, and the change in temperature across the brick is T1 minus T2, and that equals the formula for the fiberglass. But of course the change in temperature there is T2 minus T3. We can now rearrange to find XF. We multiply both sides of the equal sign by XF. We divide both sides by the KB multiplied by T1 minus T2 in brackets, and we multiply both sides by XB. That rearranges to find XF. And then inserting the values we can determine XF, which is approximately 33.2 millimeters. So a slightly different approach to a solution in this particular case to that of some of the previous questions. I would encourage you to start the presentation and just think through the process involved here to calculate XF. That's the thickness of the fiberglass. Finally, question 3, solution continued. We're required to calculate the heat transfer rate through the new fire brick thickness and the fiberglass configuration. So lowercase q here is calculated, but using the thickness of XF we found on the previous slide. So the value of Q is 1400.5 watts per meter squared. Question 3, solution continued. This is purely for reference, so I'm going to leave this for anybody that is interested. It's just another way of calculating the value of T2 by manipulating the equation algebraically. So as I say, it's purely for reference, another way of calculating the value of T2 in this particular question. It obviously compares to exactly the same value we calculated in our previous solution. And finally, some further tutorial questions. Question 1, shown here. I'll let you review this at your own pace. Answer stated in the square bracket here. And question 2, and again I'll let you read this at your own pace. Answers again stated in the bracket. Here's the bibliography used to help generate the presentation, which I hope has been of interest to you, and as always, thank you for viewing.